Okay, so hello everyone. So I'm Bian Xing from the Chinese Academy of Sciences. I'm be here to introduce briefly about the very sensitive vibration sensing technologies based on superconducting effects. Actually, this technology was originally from gravitational waves detection in the early ages. At that time, we use Weber bonds to detect gravitational waves, and this superconducting this technology was to detect the very tiny vibration of the Weber bond. So it's basically based on three effects of superconductors. The first one is Maselli effect. This is very familiar to maybe all of us. It says that when a superconducting object, when an object becomes superconducting, it will exclude all the magnetic field inside it. So in other words, it will change the magnetic field distribution in the space. So let's just remember this. We will use it later. So another thing is flux quantization. As a result of flux quantization, the flux inside a closed superconducting loop is a constant, so it's conservative. So the third one is a superconducting quantum interference device. This was known as the most sensitive magnetic field detector, that it can detect a magnetic field change so as weak as 10 to the minus 15th to 10 to the minus 18th. So here comes the idea that, if we can convert any signal that we want to mirror to magnetic field, then we can use squid to detect it with very high sensitivity. And so here is our way of doing that. So can you see this red spot here? Hi. So can you see my pointer, a red spot?
Yes.
Oh,
yes.
Okay. Thank you. So here is a way of doing that. So we just consider a system with a superconducting test mass and a superconducting coil that carrying persistent current. So since the superconducting test mass is superconducting, so when there's a acceleration that drives the test mass to move with respect to this coil, and this will change the magnetic field distribution generated by this coil, and correspondingly changing the inductance of this system. So as we all know, flux is the product of inductance and current. If the inductance changes, the current has to change correspondingly to keep the flux constant. And so now we have converted the acceleration signal to current signal. And the current signal goes through this small coil and be converted into magnetic field signal. And then we can use squid to detect this magnetic field signal. And as a result, this acceleration can be detected with very high sensitivity. And this the intrinsic noise was described by this formula. Here, the M is mass of the superconductor of the test mass, K is the Boltzmann constant, and T is the temperature of the system. And omega 0 is the resonance counter frequency of the test mass. Q is the quality factor of the system. And C is a percent of signal energy that was coupled to the squid. And EA here is squid noise. So with very conservative parameter designs, say M, the test mass is 1 kilogram, temperature is liquid helium temperature, which is 4.22 Kelvin, and the quality factor is 1 million. Actually, that niobium at 4.2 K have reached over, I think over 10 to 7, over 10 million. So 1 million should be achievable. So the C can be 25%. And the EA is 5 times 10 to the minus 31. This is just the I think the level of commercial speed. There's some part on market you can directly buy that. So with these parameters, if your resonance frequency of your test mass is 10 hertz, you can get the acceleration sensitivity to of 10 to minus 13. So 10 hertz means a very stiff spring. So when acceleration comes, the test mass is very difficult to drive. If you can lower the stiffness, make the test mass more free, then say you can lower the resonance frequency of a test mass to 0.03 hertz, then the noise level can be lowered to 10 to minus 15. So this make this technology the one of the most sensitive vibration sensing technologies. But of course, this is very shocking that 10 to minus 15. On the Earth, we all know that the seismic background on the Earth is 10 to minus 7. We can, it's simple speaking, it's 10 to minus 7, which is many orders higher than the sensitivity of the superconducting sensing, vibration sensing technology. So if we really want to realize this, it's a sensitive goal, we have to find a way to solve to overcome the environmental noise. So here is our way of doing that. We use such a superconducting current, superconducting sensing circuit to couple two test masses, and the sensing current on the two sides was the direction and amplitude was precisely adjusted, so that when the environmental comes, which is common mode that drives the two test masses to move together, but the signal current produced by the two sets have the same amplitude but a different sign. So they cancel out in the middle path where squid is. So squid wouldn't see any environmental noise. But what you want to see, maybe gravitational waves, that gravitational waves cause the two test masses to move, you can see this. So you didn't lose any of the signal you want to see, but you just get rid of the environmental noise. So with this in mind, we developed as a detector. So this detector was originally designed to test the inverse square law of gravity. Before Yukawa and other theorists said this gravity does not follow an inverse square law. So we wanted to test it. In this detector, we use a mechanical spring suspended niobium plate as our test mass. And this test mass is very small and its weight is only less than 9 grams. And this resonant frequency is 13 hertz, and it's very stiff. And the temperature is liquid helium temperature. The quality factor is not too high. It's 10 to 20. It's about 10 to 20. So with these four parameters, our result is not that bad. So the figure on the left side is what we record. The right curve is the environmental noise. You can see it's pretty noisy there. And the red curve is the differential output. Actually, the blue line, so the blue curve is just smaller than 1 pixel. So we make it a secret so we can see that. And on the right side is the amplitude spectrum density of the noise. We can see the blue line, the blue curve that at 1.5 hertz, we got the noise level as low as 10 to minus 10, which is about 20 times higher than the intrinsic noise. And correspondingly, the differential displacement noise is on the order of 10 to minus 14s. But we can see this is very far from what we said at the beginning, that 10 to minus 13 or 10 to minus 15. So the reason is that this test mass is very small. So small test mass will give you higher noise. And the quality factor is low. It's only 10 to 20K. So lower noise, lower quality factor just means a faster, the the resonant energy, the energy the energy stored in the spring become heat very fast, and the power is high. So they give you a lot of thermal noise. The high stiffness is so as we remember that the test mass frequency is 13 hertz. It's very stiff. It's very difficult to push, and low common mode rejection ratio because the geometry errors make that the common mode rejection ratio is not so good. Another thing is the test mass was magnetic. It was spring levitated, spring suspended, so it only have 1 degree of freedom. It can only move freely along one direction. So we want to improve this. So the reason we want to improve this technology is that, so first we are developing a prototype of a superconducting earthquake early detector. This detector is to detect the gravity perturbation produced by earthquake. So this signal propagates with the speed of light. It's much faster than the speed of sound. So we can send out the warning messages to people much earlier than traditional technologies. But this is very challenging because the sensitivity of a detector needs to be as high as 10 to minus 15, which is much higher than what we have achieved, much better than what we have achieved. So the second one is it's a technology demonstration of superconducting omnidirectional gravitational wave radiation observatory, which is SAGRO. This was proposed by Professor Ho Jian-Pak in University of Maryland. This is a super large superconducting gravity gradiometer. It's to detect the gravitational waves of so between 0.1 to 10 hertz. And this requirement is even challenging. It's even more challenging. So, and it needs the displacement sensitivity to be as high as 10 to minus 18. So the last one is a technology demonstration of equivalent principle test in space station. So we have made a proposal to test the equivalent principle to 10 to minus 16 on the Chinese space station, and this requires the acceleration sensitivity to be as low as 10 to minus 14, 10 to minus 14. So to to meet this requirement, so we come back again to this formula. What we should do? Yeah, of course, the first one is we want to increase the test mass, the weight of the test mass. For the first one is only 8.7 grams, it's too small. So we want to increase this. So, and then we want to have higher quality factor to lower the thermal noise and lower the levitation stiffness. So make the test mass to move more freely. So it can be more sensitive to the signals that drive it. And also lower temperature and the better speed, because now we have much better speed, maybe 100 times better than what we are using. Of course, they are still in labs. It's not a commercial part. And other things is to reduce.
Hello, can you hear us? Hello, can you hear
Hello.
us?
Sorry. So
Yes, go ahead.
Okay. Sorry. So if you want to have a high conmode rejection ratio, so you need to match the two parts of your gradiometers, the two accelerometers. When their frequency are perfectly matched, then the response to environmental noise are perfectly the same. So they can be subtracted from each other. If they are not matched, then your CMR, your conmode rejection ratio, cannot be very high. And another thing is align up the sensitive X. If you want the two accelerometer have the same response to environmental noise, their sensitive X must be perfectly aligned. I think this is also a problem in LGWA. I think we need to know the direction, the sensitive X of our accelerometers. The last one is a full tensor detection. It's just an additional benefit. So here comes our design. So our way to improve the sensitivity is using superconducting magnetic levitation to levitate our test mass. So first benefit is that we use a magnetic field, but not mechanical springs to levitate the test mass. This decoupled the vertical direction and the horizontal directions. You use levitation, the magnetic force to overcome the gravity, and the test mass can still move freely along horizontal direction. So this increases the sensitivity of our detector. And then the second one is there's no spring, there is no deformation of material, so there is no inner fraction. So the quality factor can be very high. So this lowers the thermal noise. The third one is tunable resonance frequency, because the test mass is levitated by magnetic field. So we can adjust the current in levitation coils to increase or decrease its resonance frequency and match the two test masses inside the detector. So the fourth one is we have more degree of freedom, because each test mass have all 6 degrees of freedom. So with only 2 test masses, we can measure 5 complement of gravity gradient. So in the past, if we have 6 test masses, we can only measure 3 complements. We also, before we use the magnetic levitation, so we can adjust the distribution of magnetic field to change the sensitive X of our detector. So we can align the sensitive X very precisely. This increases the conmode rejection ratio. Yeah, I think I have talked about this, so I just skipped this slide. This is our result. In our experiment, we use superconducting using a magnetic field to push the part of test mass, push it to move. So our result is that once we change in 0.1 milliamperes of current, we can change the position of the test mass by 30 nanometer. So this corresponds to our system. This corresponds to orientation precision of macro radius. This will improve. This can improve this alignment of sensitive X by 2 orders of magnitude compared to the detector we have now. So this is our detector, and this one is the frame where the test mass will be suspended. These are this sensing and levitation coils. And so all of them have a multifunction. So they are used for both sensing and levitation. And this one is for the vertical direction to overcome the gravity of the test mass. This is also superconducting coil. This is partly a symbol of our detector. This is a fully assembled detector or detector. And this is a vacuum system, and this is a graduating system and the electronics. Actually, we have got some result. Firstly, we have levitated a test mass of about 0.5 kilogram compared to our first detector, which is about 9 grams. We have improved quite a lot. And the resonance frequency was lowered from 13 hertz to 0.6 hertz. And this frequency can be adjusted from 0.6 hertz to 3 hertz. And the lowest, actually we can lower the frequency. We can make the frequency even lower, but it's limited by the leveling. Our detector was put on wooden floor. Yeah, that's not the right place to do that, but because we lack of space. So we just have to put it in a lab of wooden floor, and the leveling is not stable. So it was limited to 0.6 hertz. And the quality factor is only 4K to 10K. The limitation is mainly limited by the residual gas, because when we adjust the current in the coils, we use heat switches, and there need to be some residual gas as heat exchanging gas. So this makes some damping, make a lot of damping to the test mass. So the test mass, the quality factor is low. If we pump this gas out, I think we can get a much better quality factor. And every test mass have all 6 degrees of freedom. So according to what we have get, we can calculate that this detector will have a sensitivity of 10 to minus 14 between the frequency band of 0.01 hertz and 10 hertz. So with the technology we already have, so what we can contribute to LGWA? So I think the first one is a squid displacement radar. Since the LGWA is already decided to deployed in the PSR, where it's very, very cold. It may be the background, the environmental temperature is just 30K or something like that. The cost to cool our detector from 30K to 5K is much, much lower than cool it from 300K to 5K. So I think it's nature to make the squid displacement readout as a backup to laser interferometry. So, and the second one is the superconducting levitation. Of course, I'm not, I do not mean that we will levitate the test mass with, it's a real superconducting levitated test mass. I think it's a mixture of Watt's linkage and the superconducting levitation. For just like here, if we have an additional superconducting coil here, when we store some current here, we actually overcome partly overcome the gravity on the left side of the test mass. So it weaker the pendulum effect, but this inverse pendulum effect does not change. This will lower the frequency of the detector. If you want to increase the frequency, we can have another coil on the top. If you store current there, you can increase the resonance frequency. By doing this, I think you can tune your detector to the I mean, it just means that you can change the most sensitive frequency band of a detector. So if you are interested in some signals, their frequency are different, so you can change your detection sensitivity.
Xing, you have 5 more minutes.
5 minutes. Okay. Yeah. Okay, so actually we have already started to do something to try out our thought. This is our new gravity gradiometer. It's a mixture of Watts linkage and the superconducting magnetic field levitation. And the frequency is tunable with magnetic levitation. And so in this detector, in our detector, the inverse pendulum effect is dominant. So at room temperature, this test mass is not free. It just slide on. It's sit on one side of the sensing coils. When it's lowered to its when it's superconducting, we can store current to push the test mass to center the test mass to make it free. So by doing this, we hope we can make a very sensitive gravity gradiometer. And this other parts is already in the factory and the machining. So we hope we can, if everything goes smoothly, I think we can try it out within 3 months. And I see many people are interested in the superconducting coils. So I just added several photos of what we are doing. So this one is a superconducting made of niobium foil. So it's not a deposited foil. It's just a metal foil. We glue it to a ceramic plate and then use laser to cut some slot. And finally, we make this coil. This coil has been tested in a superconducting thermometer, and it works well. And this is the coil under microscope, and this one is a superconducting coil that we are using now. It's a traditional way of doing that. It's just using superconducting wire winded coil, and this one works pretty well, but it's difficult to make. It's very slow to make these things, and this is the quality check and under the microscope, under our microscope. So of course, this so making this coil with the deposited foil is also very attractive to us, but our mostly our current is very high. Sometimes higher than 1 amperes. For levitation, sometimes it's about 10 amperes. So maybe this deposited foil is too thin to carry such large current. So we developed our own way of doing that. For this work, we hope we can directly help LGWA, help the spectrometer of LGWA. Okay, that's all my talk. So thank you for attention. I need to make some acknowledgement is that the inverse square test experiment is not done in my lab. I did that in University of Maryland with the supervisor of Ho Jiang Pak. And for the Watts linkage, I benefit a lot from the discussion with jurists. Yeah, that's all. Thank you.
Are there any questions?
Yeah, please.
Hi. Yeah, nice talk. I have a question. For the heat switches, is the air mandatory, or is there another way to deal with that? It sounded like as if you needed the air for the heat switches.
I think you must have heat switches because you have to open the superconducting loop to store current there. So you must have that. But since for LGWA, for the seismicrometer design, we already have the heat switches generate very less heat, not as ours, because we have a huge current there. As we said here, it's 8 amperes, and it's a large coil. The magnetic field, the magnetic energy is huge. So once the heat switch is on, the magnetic energy will deposit on this resistor and generate a lot of heat. So I need exchanging gas there. For LGWA, I'm sure you don't need such large current. and the exchanging gas is not really necessary.
Ah, okay. Okay, thank you.
Thank one more question.
Yeah, even if you need something of it, as I understand it, it's only during the loading, for example, of your persistent currents and these kinds of things. So once you're in operation, you don't need it, right?
No, we don't need it. Yeah, once it's operation, so it's no, we don't need the heat switch anymore.
And you reload. Yeah, sure, yeah.
Oh, sorry, Joris. I missed some of your question. Maybe my signal is not so good.
I thought the persistent current eventually dies out and we need to recharge it.
Sorry, it seems I didn't understand what you. Can you repeat the question?
In the sensing coil, there is a persistent current which you load with your heat switches and then you disconnect. That persistent current would not sustain forever, no? So it would die out after some time.
Do you mean that how to load the persistent current in the sensing coil?
Yeah, I just mean to say that the heat switches are necessary and you would need to use them again and again to load the current.
Yes, but a heat switch is just a heater, so it will be there once you finish building your detector. It's there all the time. Just we don't use it, so it just it does not generate any heat.
Yeah.
Okay.
Yeah, thanks.
Yeah. Okay.
Are there any more questions? Okay, if there are no questions, let's thank speaker.